Imagine an arrow floating in space. That arrow could tell you how fast something moves, the forces acting on it, and which way it's pointing. Those arrows are called vectors, and they're a core idea in physics and engineering. In this video, you'll learn how vectors work, how to represent them, and how to add, subtract, and multiply them. Let's start with a basic definition for vectors. Vectors are simply objects with both magnitude and direction. The length of our arrow is the magnitude of our vector, and the way the arrow is pointing is the direction. The Cartesian coordinate system is where all vectors live. The system has three perpendicular axes, x, y, and z. There are some special vectors that are parallel to these axes that have a magnitude of 1. These are called basis vectors, and they're known as I, j, and k. The basis vectors are very important because all vectors can be described as a combination of them. Let's use this vector as an example. It has 3 units of I, 2 units of j, and 1 unit of k. We describe this vector as the sum of all the i's, j's, and k's, but this is often represented in shorthand with just 3 numbers, usually by a column matrix or by using these triangular braces. Vectors can also be defined as the displacement between 2 points. The components of the vector can be found by subtracting the start point from the end point. To subtract a point from another, just subtract component by component. For instance, subtracting the x components of these 2 points results in 2 minus 1, resulting in a vector with one I component. Vectors are not anchored in space. They can be moved around freely. You can slide around a vector anywhere you want, as long as its length and direction do not change. Let's talk about how to find the magnitude of a vector. Take this 2D vector for instance, 3i plus 2j. Again, the magnitude of a vector is just the length of the arrow. Therefore, the vector magnitude can be found using Pythagorean theorem. The notation for magnitude is 2 vertical lines. Just sum the squares of the x and y components and then take the square root. In this case, the vector's magnitude is square root of 13. If this were a 3D vector, we just have to add the square of the vector z component. Now that we know about magnitude, we can talk about scaling vectors. It's actually pretty easy. You just multiply the vector by a scalar. The magnitude will also be multiplied by that same factor. To carry out the multiplication on the vector, just distribute the scalar to each vector component. Here are some other examples of scaling a vector with other factors. Notice when a vector is scaled by a negative factor, the direction of the vector flips. If we divide a vector by its magnitude, we get what's called a unit vector. A unit vector retains the same direction, but has a magnitude of 1. And instead of an arrow over our vector symbol, we use this hat for unit vectors. You'll notice this hat was also used for our basis vectors I, j, and k, since those are also unit vectors. Now let's talk about adding and multiplying 2 vectors. Adding 2 vectors can be thought of as putting the vectors tip to tail. The result of the addition is the vector drawn from the tail of the first vector to the tip of the second vector. Algebraically, vector addition is simple. We just have to add each vector component together. There are 2 types of vector multiplication, the dot product and the cross product. The dot product of 2 vectors is calculated by multiplying each component together and then summing all of the products. Therefore, the result of the dot product is a scalar. The angle between the 2 vectors is related to the dot product. This relationship is useful because it means we can calculate the angle between 2 vectors quite easily. Like in this example, we can find that this angle is about 133 degrees. The cross product is found by taking the determinant of this 3x3 matrix, with the first row being our basis vectors I, j, k, the second row is the first vector being multiplied, and the third row is the second vector being multiplied. If you don't know how to do this determinant, don't worry, I'll show you in the next section. What I want you to know is that the cross product returns a vector, perpendicular to the two input vectors. If you take your right hand and align your index finger with the first vector of the cross product, and your middle finger with the second vector, then your thumb will point in the direction of the cross product result. This is known as the right hand rule. The cross product also has a relationship to the angle between the vectors, but finding the angle this way is more work than just using the dot product. The order of multiplication matters for the cross product. If you flip the order of vectors being multiplied, you get the exact opposite result. Okay, back to that determinant. This method for taking a 3x3 determinant is known as the crisscross method. Take the first two columns of the matrix and extend it like this. Now we multiply the elements along each of these diagonal lines and add them together. Then we subtract the products found by drawing diagonal lines going the other way. Finally, just group all the like terms together and you're done. Finally, let's go over the properties of these two products. First, both the dot and cross products are distributive. Are they commutative? Well, the order of multiplication does not matter for the dot product, so it is commutative. But the order does matter for the cross product, so it is not. The cross product is anti-commutative, since changing the order of multiplication returns the negative result. How about associative? Well, the dot product returns a scalar, and then we can't do the dot product of a scalar and a vector, so we'll just say no. The cross product is also not associative, because the result changes based on the order you carry out the multiplication. Thanks for watching. I hope this helped you with the basics of vectors. If you found this video helpful, consider subscribing or leaving a like, and I'll catch you next time.